bad and a wicked and bad, 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 bad.
Today's lecture is going to be about tree indexes, specifically B+ trees, which we'll get to in a moment. Just really quickly, I just want to remind everyone about some upcoming deadlines. Project number 1 is going to be due this coming Sunday, September 26th, as usual at 11:59 p.m. And homework number 2 will be due Sunday, October 3rd at 11:59 p.m. So those are the deadlines, and now let's jump straight into the material. So last class we kind of talked about hash tables and how data structures could be leveraged in all these different ways in our DBMS. So again, you could use it for internal metadata storage. You could use it for core data storage at the level of a table. You can use a hash table as a temporary data structure, and we also mentioned that it could be used as a table index. But specifically, what we're going to focus on today is table indexes, and we're going to discuss why you may not want to use a hash table for that purpose, and an alternative data structure called the B+ tree that is more widely used for that use case. So just so we're all on the same page, a table index refers to basically a replica of a subset of a table's attributes that are organized or sorted for efficient access of those based on those attributes. So this is going to allow the DBMS to quickly find data that we're looking for. For example, if it's a primary key, we can quickly track down the data that we're looking for. Whereas the alternative, if we didn't have a table index, would be to perform a sequential scan of the whole table. So we'd have to read the whole table, all the pages, to find all of the tuples that we're looking for. If you have something like an OLTP or transactional workload, you almost always will need some form of table index because, as we kind of discussed in previous lectures, those types of workloads rely on low latency access. So you need to be able to get to the data items that you want very quickly in order to read or update them. So you need some kind of index to get that latency. Otherwise, you're stuck again, kind of performing a full scan. And with the table index, the DBMS is going to be responsible for ensuring that the contents of the table and the contents of the index match. So they have to be logically synchronized. We can't have updates, insertions, deletions applied to just one and not the other, because then if we go and look up something in our index that's been removed from the table, we haven't yet removed it from the index, then it's going to point it to some garbage value. If it's the other way around and we go to look something up in the index that's been only inserted in the table, but the index hasn't yet been updated to reflect that, the index is going to tell you it's not there. So kind of the DBMS needs to keep track of keeping the contents of these synchronized, and we'll talk about that in later lectures when we focus on transactional properties. So during runtime, it's the DBMS's job to figure out kind of the best index or indexes to use to execute each query. So picking kind of the process of picking these correct indexes is part of what's called query optimization. Again, we're going to talk about that in later lectures, but the key idea is that there are potentially a bunch of different ways to execute a particular query. So the DBMS is going to have to pick the best or fastest way to do that. And in terms of building indexes, there's this trade-off that we have to keep in the back of our mind regarding the number of indexes that we're going to create per database or per table. Obviously, the trade-off is that we get faster lookups. If we have indexes built, then we can use them to speed up our queries. But on the other side of things, we have to pay in terms of storage overhead. So we have to store some extra data, metadata, the data structure itself, in order to build the index, and then we also have to pay overhead in terms of maintenance. So this process of keeping the index up to date and synchronized with the data that's stored in the base tables. So kind of just in the back of our mind, we're always trying to balance these two things, kind of the speeding up our queries as well as these overheads that we need to consider. So just a high-level overview of today's agenda. First, we're going to talk at a high level, what is a B+ tree? Then we're going to dive down into how we can actually use them in DBMS, some of the different design choices that we need to consider when building the actual data structure, when we're designing the data structure, and finally, just a few optimizations that we can apply to improve our B+ tree implementation. These aren't going to be, all of the possible optimizations. There are a lot out there, but just a few examples. So the B+ tree is by far the most commonly used type of index for a DBMS. So the first thing that we kind of have to talk about is this confusing naming scheme. There is a class of data structures or family of data structures called B trees, and there's also a specific data structure that is called the B tree. So specifically in this course, we're going to talk about the B+ tree, but people, broadly use the term B tree to refer to any of these different balanced tree data structures. So the B-link tree, for example, which I think came out of CMU, kind of has some ideas where leaf nodes have these pointers that link between them, which we'll see in a few slides. But kind of the modern B+ tree borrows ideas from all these others. So it borrows ideas from the B-link tree, borrows ideas from these others. So we're going to be, in this class, specifically referring to B+ tree, and I will try not to slip up and use the B tree term, because specifically we're going to be talking about B+ trees. If you're wondering what the B in B tree or B+ tree stands for, I couldn't tell you, so am I. The authors of the paper never explicitly stated what the B stands for. People have, speculated over the years that maybe it stands for balanced, broad, bushy. One of the authors' name was Bayer, so it could be, his name, or they also worked at, but yes, it was Boeing Research Lab. So the B could have been, any one of those. I unfortunately can't give you a definitive answer on it. So as I said, the B tree is, or B+ tree, already starting. The B+ tree is the most widely used data structure for indexing in DBMSs. Pretty much when you call create index in almost every DBMS, you're going to get a B+ tree or something very close to it in the behind the scenes. So again, just to summarize, the B+ tree is a self-balancing tree data structure that's going to keep the data sorted. So it's going to allow us to perform searches over the sorted data. It's going to allow us to perform, lower bound or upper bound searches. We can find ranges in the tree, which we weren't able to find in the hash tables that we discussed. And we can also perform insertions, deletions, and all of this in log n time complexity. So you can think of it just, as a generalization of a binary search tree with multiple child nodes. So whereas a binary search tree has just two, you can have more than two children in a B+ tree. And specifically, it's going to be optimized for systems that read and write large blocks of data. So we've been talking a lot about accessing data at the level of disk pages, and that is going to be the particular use case that this data structure excels at. So there's no original B+tree paper. Most people cite this. It's a survey paper from 1979. And it mentions that there's this IBM technical report that actually described a B-tree, B+tree in 1973, I think it was. But I can't find it, and no one that I know can find it, so it's kind of lost to history, I guess. So kind of this is the paper that everyone references when they're talking about the B+tree. And even though this data structure we've seen is like most of the original publications are from the 1970s, as I said, it's still widely used today. So kind of the properties, the theoretical or formal properties that we care about with the B+tree, it's an M-way search tree where M is the number of branches emanating out from a node. Sometimes this is also referred to as the degree or the branching factor or the order of the tree. So this is the number of branches or child pointers coming out of a node. The properties, again, that we care about are that it's perfectly balanced so that every leaf node is at the same depth in the tree. Every node other than the root node is at least half full, and every inner node with k keys has k plus 1 non-null children. So if we have k keys in a node, there's going to be one extra child, and we'll see why in a second. So here's a visual example of a B+tree with some integers inserted into it. It has a degree or order of 4 because it has 4 child pointers emanating out of the root node. These nodes along the bottom we refer to as leaf nodes. And this node up here is an inner node. Since the tree only has 2 layers, it's the only inner node is also the root node in this case. So we're also going to have at the leaf node layer, we're going to have these sibling pointers that essentially turn the leaf nodes into a linked list or a doubly linked list. So we can traverse along the leaf nodes in the tree, and we'll see why or ways that can benefit us later. And the way that the keys are stored in the nodes are as this kind of a pair. So this really thin double line is a node pointer, so that refers to a child node. And the key is stored next to it. So as I said, if there's going to be 3 keys, there are going to be 4 child pointers. So you can think about kind of these keys that are stored in the inner nodes as being kind of the dividing point between each of the child nodes. So for example, if we look at this tree, we see that all of the value or keys stored in the child node to the left of the first key 5 are going to be less than 5. All of the keys stored between 5 and 9 are going to be greater than or equal to 5 and less than 9. And all of the keys stored to the right of 9 are going to be greater than or equal to 9. So at the child node, the leaf nodes, we're storing the actual keys along with their values. So we'll talk about exactly how the values are stored later, but in the inner nodes and the root node, we're going to store keys and node pointers. At the leaf nodes, we're going to store keys along with their associated values. So are there any questions kind of at a high level about this right now? And then we'll go through some of the lower level details in a minute. Yes? So there's nothing really like on the right? So the question is, there's nothing really on the right of things, just always to the left. Yes, so the space to the right is used for inserts, and then as you fill up, you may need to split nodes. But yeah, so everything gets inserted in a sort of left aligned. Yes. So every B+ tree node is comprised of an array of key value pairs. So the keys are somehow derived from the attributes that the index is based on. So that could be like a primary key, it could be a combination of multiple keys. We'll see an example of that in a second. But kind of the keys are based on whatever attribute you're indexing. And the values are going to differ based on whether the node is classified as an inner node or a leaf node. So again, the inner nodes are going to store child pointers, and the leaf nodes are going to store the actual values or references to those values. And the arrays inside each node are usually kept in some kind of sorted order for the keys, so you can search them quickly using binary search or something. We'll talk more about different search patterns or search algorithms for within nodes later, but there's no rule that says you have to maintain sorted order inside one of these nodes. It just depends on what your later search algorithm is going to be. So the leaf nodes specifically, if we zoom in on what that looks like, conceptually we've been sort of visualizing it in the previous slides this way. So there's going to be at the beginning and at the end some pointer to the previous node and a pointer to the next node. And we're also storing these keys, so K1 through Kn, and the associated values. So usually these pointers aren't actual pointers or references to memory locations. Usually they are just references to the page ID that represents the next node in the tree. Again, having these keys and values stored here, there are different ways to do this, and we'll go through some options for how they're stored. One way is to, as shown here, physically store the value inside the node contiguous with the keys. Another option is to instead replace the value with a pointer or a reference like a record ID that tells us where to go find that value associated with the key somewhere else in the table storage or something. So yet another way we can physically lay this out, and this is how the storage is typically done. You store some header or metadata at the top. For example, the level in the tree, the number of slots that you have, the previous and the next pointers, and then you store the sorted keys in some kind of contiguous array separately from the value pointers here. And this allows you just to have better sequential access when you're searching through the sorted keys. You don't have to worry about, is this next thing a value, is this next thing a key? You can just kind of have all of the keys grouped together and then all of the values grouped separately. So again, kind of these keys, if we know that key 4 is at that offset, then we can kind of look at the corresponding position in the value pointer array with very little overhead. We don't have to search for that one again. So as I said, there are different ways that we can store the values in the leaf nodes. Approach number 1 is to just store the record ID, which is basically, you can think of like a pointer to the location of the tuple that the index entry that the key is referring to. The other option is you can kind of store the full tuple data right in the leaf node with the key. So in this case, the leaf node, there's not some kind of other data structure that like a table or something that's maintaining the data. The tuple actually lives in the index, and the problem is that this is only going to work for the primary key index. So if you have a primary key and you have your table organized in some order by that, then that can live inside the index. But if you have a secondary index, you have to store the record ID. So you can't have kind of these multiple sort orders, because otherwise you're duplicating data, and you need to keep it kind of consistent across all of these places. So there are various systems that do things different ways. Some let you do both. But the high-level point to take away is the safest thing to do is to kind of have this record ID pointer rather than this. It's called a clustered index in the second approach. So I made this big deal at the beginning that. Sorry, there's a question. Yes.
Yeah, I just had a question. So you said that the record IDs, you could consider them linear to location of the tables, but if they are on like a remote machine, how does that work?
So the question is, if the record IDs are pointers to the tuples, if the tuples are on a remote machine or something, how would that work? So we're not up to distributed databases yet. Basically, so the way you can think about this is just kind of if you have some combination of a page and an offset in the page, that represents the tuple's record ID. So you can go find it. If it's local, then all you need to do is get the page, go look up in the page directory, get the page. And then you can find the offset directly inside the page. I suppose if you had some kind of distributed database, you would need some kind of global mapping where pages reside on different machines in your distributed setting. So, just based on that page ID, you could go track down where the page is, request it from a remote machine, get it back, and then you still have the offset in the page is the same. Does that make sense? Right. So I made this big deal at the beginning that there's a concrete difference between a B tree versus a B plus tree, and that we're specifically talking about B plus trees. In the original B tree paper, the keys and the values could be stored in all nodes in the tree. So as we saw in the previous examples, we just had, for the inner nodes, we just had the keys stored and then pointers to child nodes. And then when you get to the leaf nodes, that's where the actual values are stored. In the original B tree, you could store keys and values in any node in the tree, inner nodes, the root node, wherever. So the trade-off here, it's more space efficient since each key only appears in one spot in the tree. But the difficulty is that it's harder to support concurrent access of keys. So if you have potentially keys and values at all these different spots in the tree, then you have to now concurrently manage updating nodes anywhere in the tree rather than just at the level of the leaf nodes. And we'll see why, especially for insertions or deletions, that becomes trickier as we go a few more slides in. And the other problem, if you have kind of these key value pairs scattered throughout the whole tree, is that it can cause problems for your access patterns. So we've also been talking a lot in the course about that particularly for disk-based systems, we prefer sequential access patterns over random access patterns. If you have kind of keys at various places in the tree where you need to retrieve them, you could end up with some random access patterns. Whereas if the keys and values are only stored at the leaf node layer, then you can get a sequential scan across those at the bottom. So kind of that's the main key takeaway here. The important difference is that the B plus tree is only going to store values in the leaf nodes, and the inner nodes, again, the keys stored in the inner nodes are only used to guide the search process. So they're only used as sort of these split points where when we're searching for a key in the tree, we can say, is the key, you know, greater than or less than this particular split point. So the DBMS can use B plus tree in a few different ways. If the query is referencing any of the attributes for the indexed key. So for example, if we have an index built on keys A, B, and C, then we can support operations that are, you know, of the form A equals 5 and B equals 3. We can support operations of the form just, you know, A equals 5 or just B equals 3. As I mentioned earlier, the B plus tree can also handle other comparisons beyond just equality. So you can do greater than or equal to, less than or equal to, unlike a hash table, which can only do exact match lookups. So not all DBMSs are going to support these types of selection conditions. It becomes kind of tricky if you have multiple indexes or indexes built in different ways to figure out the best combination to use. But kind of the key idea is that we can leverage the indexes during query processing time, during our query optimization phase, to figure out the most efficient way to execute the query. So just as an example of how this would look, let's say we want to find key A, comma B. So those are the two values that we have set, and we have the keys stored in our B plus tree here. So we can go to this root node and we say, okay, is A, the first piece, less than or equal to A? That's true. Is B, the second piece, less than or equal to C? That's true. So we know that we only have to traverse down here and look in this node. So this is like a kind of a full lookup for the key that we're looking for. So we get down to the leaf node, and then we can search in the leaf node for the exact key that we want to find. The second type of lookup we can perform, I mentioned, is this kind of like a prefix lookup almost. So we're searching for anything that kind of matches this pattern, where the first key is A and the second key can be anything. We don't care. So we just want to find, you know, all keys that match this A and then wildcard pattern. So again, we go to the root node here and we say, is A less than or equal to A? Yes. So we're going to traverse down this path here to the child node. And then we kind of just need to scan forward to find all of the keys that match this A wildcard pattern. And since we have these pointers that point between or link the leaf nodes, we can just scan straight across and stop as soon as we find a key that's larger than A star. So are there any questions about this? Yes? Sorry, can you repeat the question? So this second, yeah, okay. So the question is, we can also support a search on just B equals something. So I'm not showing it here. The way that it would work is you would need to search in all of the nodes that could possibly contain that value. So in this case, if we can, I don't know if you can do it with this tree construction, but imagine a more complex tree construction where you could rule out, when you're traversing the path down, you could rule out certain subranges where you know the B value can't be included. Does that make sense? So it's tough to do without an example here, but if if you imagine a more complex tree with multiple layers or different split points, you may be able to exclude certain subranges of the tree where you know that like B value isn't between two other values. Does that make sense?
But the primary construction is on here, right? So how many tables on it? If you plan to do that thing.
So the question is, if the primary construction is on A, how can you traverse down to, how can you exclude ranges for the secondary one? Yeah, so if you can get into a particular subrange, so I don't think it's going to work in this example tree here, but if you can figure out that there's no way that B can be included in a particular subrange because you know the min and max values for that subrange, then you can exclude it from search. Yes?
I think like a good example here is that if you're doing like wildcard B, for example, once you hit the CC, you're gonna look and you're gonna see anything greater than that. It's not possible to have a B in the secondary like of that tuple. So then you can like ignore that child altogether.
So the comment was that in the leaf node all the way on the right, it's not possible to have a B in the second position. I think you could in this case, because, so imagine like you have another, like if you have D comma B at the end. I think if, so I don't think that it works in this particular example here, but I think that if you have a subrange where you know that there's no way that you could have a B in the second position, and maybe we can take this offline after class, I can show an example, but if you can narrow down a particular subrange where you know that there can't be a B in the second position, you can exclude it from your search. And so this is just with two values. I mean, you can generalize to more A, B, C, and maybe that makes it a little bit easier to think about if you know that you have A comma B, and then some other value, you know that the B value, you don't have to search for something that's a C in the second position. Does that make sense? Okay, so for performing an insert, this is kind of the basic algorithm. It's pretty straightforward. Basically, we're going to find the correct leaf node L that the key belongs in. We're going to put the data entry into L in sorted order, so that's the key and either a pointer to the value or the value itself. If L has enough space in it, then we're done. That's great. Otherwise, we need to split L into two nodes, so we can take the keys that are in L and split them. Some are going to go in the original L node, some are going to stay there, some are going to go into this new L2 node. We can redistribute the entries evenly between them. And then we're going to take the middle key, so the split point, and copy that up to the parent. So then we kind of get this new split point inserted in the parent if the node grew too big. And then we're going to insert an index entry pointing from the parent down to the newly created L2. So kind of to split an inner node, we just redistribute the keys evenly, but we again push up the middle key. So it works similarly each time we want to split, for example, let's say the inner node we're splitting is the root. That's going to increase the tree height. So kind of the deletion is sort of the inverse of this. We're going to start at the root. We're going to find the leaf L again where the entry belongs. Remove that entry from the leaf. If it's at least half full, then that's great, we're done. Otherwise, we need to redistribute it, redistribute the entries somehow, either by borrowing from our sibling, or merging a node and the sibling. So we need to maintain this property about the fullness of the node. So then again, if the merge occurred, we go up to the parent and we have to delete the pointer to the node rather than adding it as in the insertion case. And again, this merge can propagate to the root, which will reduce the tree height. It'll decrease the height by one layer. So one of the problems that we can run into, and we talked a little bit about this with hash tables, is dealing with duplicate keys. So the first approach is really simple. We just append the record ID to the key that we're indexing. So we just take the unique record ID, let's say it's the page number and the offset in the page, and we'll just kind of stick that on the end of the key. So now it's unique because even if the key is the same as another tuple, only one tuple can have that unique record ID. So we've made the key unique, and then we can put the key into the tree, and we can just do this partial like prefix sort to find the key that we're looking for. So the other alternative is kind of this overflow approach. So we've seen a few other cases, like in the hash tables, for example, where if we have duplicate keys, we can just kind of store them in this overflow bucket. This works similarly. I'll show you in a couple slides what it looks like. But basically, we're just allowing nodes, the leaf nodes, to spill over into an overflow node that contains the duplicate keys that we have. It's typically systems will take the first approach because the second one's a little bit harder to maintain and deal with. Especially, I mean, you could imagine if you have a lot of duplicates, you could have a leaf node grow kind of into this unbounded chain of overflow nodes. So this is going to be the first approach we talked about, which is appending the record ID. So again, we have this similar looking B+ tree to what we had earlier. Less than 5, less than 9, and greater than or equal to 9. And what we're actually storing here, instead of just the key 1, we're storing the key plus the record ID. So it's not shown here, but imagine that there's the key, so 1, 3, 6, whatever, as well as the associated record ID that uniquely identifies the tuple that we've added. So now if we want to insert 6, again, what we're really going to be doing, there's already a 6 in there. What we're really going to be doing is inserting 6 plus this record ID, which is just the page and the slot of the tuple. So now we've kind of solved the problem. We're going to figure out that it belongs in that bin. We're going to split the bin because now it's too full. So we split it into these two separate sub bins, and we can put the new. We'll update the pointers. Move the middle key up, move 7 up to the parent node, and now we can insert 6, the new 6, not the existing 6. We can insert the new 6, which is the page, which has the page slot record ID appended to it. So we can get both of these duplicate keys stored in the B+ tree, and they're still uniquely identifiable. So does anyone have any questions about this? Yes? Sorry, so the question is, you don't have to store pointers at the leaf nodes? You mean in this picture here? Yeah, so I excluded them. There should be pointers, so there are pointers there. There should be the pointers redrawn between all these. It's just got a little messy with the dagger. But there should be pointers between all those leaf nodes, yes.
So I mean that since you already have the record at the last level, so you know where to find values corresponding to this key. because you already have that record ID which is really useful.
Okay, I understand. So the question is, do you also need to store the value pointers in the leaf node because you already have the record ID stored inside the key? You don't have to store the value pointers. So that's one possible optimization you could play, because you can find out where to get to that value just by looking at the second part of the key that the composite key that we've created. I guess this doesn't necessarily help if you want to store the values embedded in the leaf node, just for ease of access. So in a clustered index, but yes, that's one possible optimization. Yes. Yes.
In this example, this key record ID pair, accidentally it's also on the leaf node layer. If it's in the middle layer, it should also be key record ID.
So the question is, do you also store the key and record ID in the inner nodes?
Yeah, it's also collided as the same thing.
I'm not sure if you need to store the key and record ID in the inner nodes, because I think you can get to the subrange that you need. I think you should be able to get to the subrange that you need, unless you fill up. Then you can collide in the inner node. Yeah. So if you fill up the inner nodes, then you can store it there as well. Yes.
This example, the record ID is also on the node, and the node also have to save the value. So this record ID acts two roles. But if it's in the middle node, should there also be this record ID? Yes.
So I think the question is, do the record IDs get stored in the middle nodes? I think the answer is yes, because imagine that you have more duplicates than fit in a page. Yeah. Because then if it needs to split based on something, otherwise you wind up with some kind of like orphaned pages somewhere. Yeah. Okay, so the other alternative I mentioned was these overflow leaf nodes. So again, imagine we want to insert 6 here. The node that it belongs in is full. So we're just going to create kind of this overflow buffer where we're going to just have a pointer that points to it on the end, and then we're just going to be able to fill it up with additional values. So we just inserted 3 values there, 6, 7, 6, and they kind of just go in this overflow buffer. In the example, the leaf nodes are no longer sorted. Again, this isn't technically wrong, but we just need to know that we can't do binary search in the leaf node, because they're out of order now. You need to do sequential search in it. Physically, these get stored in separate nodes. So there's the original node there, and then the overflow node or bucket. Logically, it just looks like one really, really big leaf node, and kind of it's easier to leave this sibling pointer on the exact neighbors, so that when we add in the overflow bucket or the overflow node, we don't update the pointer. We don't change the pointers from the original leaf node to its sibling. We just keep those pointing to the original one. Okay, so I mentioned clustered indexes. Basically, the idea is that the table is stored in the sort order specified by the primary key. So you have a primary key on your table that uniquely identifies the tuples in the table, and a clustered index is going to use that primary key as the sorting key. So this is kind of how different ways that we can use the B plus tree in the DBMS. And some DBMSs always use a clustered index. If a table doesn't have an explicit primary key that you as the user have specified, then the DBMS will automatically make like a hidden primary key. Other DBMSs don't use clustered indexes at all, so they just keep the pages or the table stored as unordered pages, and they don't have this kind of index organized table structure. So what this would look like in during query processing is if we want to perform a search, we're going to traverse the leftmost leaf page, and that's going to give us tuples from all of the leaf pages. So if you think about kind of, we have this index structure here, which is going to direct our search, and we have the data entries at the bottom, and then below we refer to these data records which are stored in pages. This is going to give us a sorted order for the table. And again, if it's clustered, then our pages are going to be organized or sorted based on the primary key. So this is going to be better than some kind of external sorting algorithm because it's already sorted in the index. So kind of you can imagine the pointers, like I said, going in increasing order across these pages, and our scan direction is going to be, we're going to be able to scan, you know, sequentially across all of the values because they're already maintained in sorted order. So on the other side, if we have a non-clustered index, so that means that the table is not sorted by whatever the key is, the primary key, or maybe there's a secondary index, then we're going to be retrieving tuples from the index lookup in the order that they appear in kind of the base page layout. And this can be very inefficient because it might lead to a lot of random accesses in the data. So just as an example of what this looks like, again, we kind of have this scan direction. So we want to perform a sequential scan from some low end of the range to some high end of the range. But what the pointers actually look like are kind of these random points. So the keys are in sorted order, but the pointers are in kind of all these random out of order, pointing to all these different pages. So we may end up fetching pages multiple times in kind of this random order, and it's not going to be very efficient for scanning the range. So kind of what the access pattern might look like is if we have all these different pages and we just do it by scanning across the index like this and accessing each tuple as soon as we find it in the index, we're going to have several page reads here, repeated page reads, where we read pages and then read other pages and then go back to the pages that we looked at earlier. So kind of one way to get around this is if the DBMS, rather than accessing tuples immediately, performs some kind of scan to accumulate all of the pages that we're going to need in advance, and then we can sort them based on the page ID so that we're only accessing pages once. So what that would look like here is, we do the scan across the index, we get all of the pages that we're going to need, 101, 102, 103, 104, and then we sort them in that order, so we only have to access each page one time. We don't have to have these multiple reads jumping all around the file because the entries are out of order. So are there any questions about this part? Okay, so there are a wide variety of design choices that we need to make when we're physically implementing the B plus tree. So far we've been kind of talking about them abstractly, but we need to make decisions about what the size of the nodes are going to be, what our merge threshold is going to be, all that kind of stuff. There's this great book, Modern B-Tree Techniques, And it covers a lot of these things we'll talk about, plus others. If you're interested, I encourage you to take a look at it. But kind of we'll just go through a few of these design choices that are pretty important when we're physically implementing the B+ tree. So the first thing that we need to think about is the node size. Kind of there's this rule that the slower the storage device that you're using, the larger the optimal node size for B+ tree is going to be. So if you're on a traditional HDD, then the optimal node size should be around 1 megabyte. Faster things like an SSD, optimal node size around, on the order of 10 kilobytes. And if you're in memory, I can get as small as 512 bytes. So kind of on the slower storage devices that have this better sequential read performance or sequential access performance, the larger node size maximizes the sequential access. So if you are reading 1 megabyte from disk, it's a lot better than reading much smaller node sizes from disk. And again, the optimal sizes can also vary depending on the workload. So if you're performing a lot of leaf node scans, that's going to be different than if you're doing a lot of root to leaf traversals. So kind of we need to consider both the hardware that we're running on as well as the workload. So the second piece I mentioned was this merge threshold. So we talked about kind of the theoretical rules for when you merge nodes when they're half full. Not all DBMSs do that. Sometimes what they'll do is delay merge operations in order to reduce the amount of reorganization they need to perform. And the idea is basically that if you're doing a bunch of insertions, deletions, maybe insertions will come along later to fill up the less than half full node that you have. So kind of delaying or deferring these reorganizations that can be performed periodically to clean up the tree without having to do it on every insert or delete that would normally trigger this kind of merge. So variable length keys are another important thing we need to think about. There are many approaches. I have listed 4 here. Kind of the first and most obvious way is just to store the pointers. So the keys are just a pointer to the tuple's attribute. We don't actually store the variable length key. We just store a pointer to the tuple's attribute, and then we can go look up wherever that's stored in a page somewhere to find out what the value is. Approach number 2 is kind of having variable length nodes. So imagine that each node in the tree can have a different size. We don't have a fixed node size. They can vary depending on the keys that are stored in them. But on the downside, this requires pretty careful memory management. I don't know of any systems that do it this way because I think it gets pretty complicated with figuring out the size of individual pages. Approach number 3 is to use padding. So basically you just allocate the maximum possible space. So imagine you have strings or something and the maximum string is 100 characters long. Even for keys that are less than 100 characters, you always allocate 100 bytes for the key. If most of your keys are all about the same length, this might be okay, but if you have one really long key that you need to accommodate and the rest are pretty short, then it ends up being pretty wasteful. And the final approach is kind of this key map indirection approach. So basically it works similarly to the slotted pages that we talked about for the disk pages, where basically you embed an array of pointers in the beginning of the node and they map to some kind of variable key length. They map to some kind of variable length key at the end, and they kind of grow towards each other in the middle, similar to how the slotted pages worked. So the final piece, and we've kind of touched on this a few times in some of the earlier slides, but is how, once we're inside a node, how we actually find the keys in the node. So again, these are just 3 examples of ways you can go about searching for keys in the node. There are many others, but these are pretty straightforward. So the first approach is just a simple sequential or linear search. So you scan the node from the beginning to the end. Imagine, for example, you want to find key 8 in this array of keys. So what we're going to do is we're going to start at the very beginning, and it's just going to be a loop going forward one key at a time until we get to key 8, and then we're done. As I mentioned earlier, if the keys are not stored in sorted order inside the node, then you're kind of stuck with linear search. There's no other way other than to scan linearly or sequentially through the keys in the node. Yes?
So are we just talking about these nodes here, or is it possible to have inner nodes which have the keys in unsorted order?
So the question is, does this just apply to the leaf nodes, or can you have inner nodes that also have the keys stored in unsorted order? I suppose you could also have the inner nodes stored in unsorted order, but you would need to look at every single key to find out which 2 keys you belong between, right? Because without looking at all of them, you wouldn't. There could be another one, that further subdivides the range. So I think yes, it's possible, but I don't think it's practical or efficient because you'd have to look at every single key. Okay, so this is linear sequential search. I'm sure everyone knows binary search. Basically, if we know that they're stored in sorted order, we can jump to the middle key, and then we can pivot to the left or right depending on the comparison. So in this case, 8 is greater than the middle key 7, so we're going to go over here and search this subrange. 8 is less than 9, so we're going to move over, and now we found 8. So this maybe doesn't look like a huge difference in the number of comparisons that we have to perform with a array of size 7. So we're looking at 7 keys. But as you scale up, if you're looking at many keys, then the difference here can be substantial. Finally, the third approach that I'm going to mention is called interpolation search. So basically, you're going to approximate the location of the desired key based on the known distribution of the keys. So again, we have this array, and basically we're going to estimate the offset based on the distribution. So you take the key that you're searching for, minus the start key, so that's 4, times the length of the array is 7, divided by the total range, and that gives us, using integer division, gives us offset position 4. So we can jump right to the position in the array that the key 8 should exist at. Now, if the distribution isn't, this is a linear interpolation. If the distribution isn't quite linear, then you may have to perform this interpolation several times, or switch to some, if you can get really close to the key initially, you can fall back to some other either linear or binary search afterwards. But basically, the idea is to just use some kind of interpolation to narrow down the search range that you're looking for. Okay, so the final piece I want to talk about is just a few different types of optimizations that we can apply in the B+ tree. I'm going to talk about prefix compression, deduplication, and bulk inserts. And there are, as I said, many, many more. If you're interested, you can either check out that book, where there are plenty of papers available that describe all sorts of optimizations of varying complexity. But these three are pretty common and I think pretty impactful. So we'll just go through a few of them quickly. So prefix compression, basically, if we have sorted keys in the same leaf node, they're likely to have the same prefix. So the example I have here are three words: robbed, robbing, and robot. Instead of storing the entire key each time, so we have these three keys stored, we can extract the common prefix that they have and store only the unique suffix for each key. There are many variations on this scheme, but basically this is the premise. We take the prefix ROB, and then for each key we store the unique suffix below it. So this, depending on how similar the keys are, we can end up saving a lot of space if there's a lot of repetition of prefix. So the second optimization, deduplication. Basically, if we have a non-unique index, we can end up storing multiple copies of the same key in the leaf nodes. So in this example, let's say we have key 1 repeated 3 times. We end up storing the key as well as the associated value. Instead, what we can do is just store the key one time and then sort of maintain a list of the tuples with that key. So similar to what we discussed in implementing the hash tables, if there are many duplicate values, we could just store the hash key once and then sort of a list of values associated with those keys. So we could transform this array here into something that's more compact that looks like this. So we store the key once, all of the values associated with the key, and then the next key. So the final optimization I'm going to talk about is related to actually building the index or performing a bulk insert. So this means imagine you have kind of like an existing table or some existing data that you want to build an index, a new index on top of. So you're not starting from scratch. You have something, a table that already has data in it. The fastest way to build a new B+ tree index for this existing data is to first sort the keys. So we get the keys pre-sorted, and then we build the index on top of the sorted data from the leaf nodes up. So kind of the way we've been talking about inserting into the tree or expanding the tree so far is by starting, we always start at the root node and we work down until we find the leaf node that the key belongs in, and then kind of we perform the insert from there. In this case, we're starting from the leaf nodes, so we take the data, sort it, and then we can build the leaf nodes efficiently, as well as then subsequent layers of the tree. So imagine we have these, this pre-existing data, these keys. The first step that we want to do is sort the keys, so we get them in this sorted order, and then it's more efficient for us to just kind of scan along here and insert them into some nodes. We, of course, build the sibling pointers between them, and then we can build the upper layers based on these values. So kind of this way of performing a bulk insert or a bulk load allows us to be much more efficient than having to check all of the logic of traversing the tree, performing splits on every single insert. So are there any questions about any of these optimizations that we've talked? Yes?
This is not an advantage if you are sort of doing a bulk insert rate, but already existing index. Once you have an existing index, you build up into a bulk stuff. Are there any efficient ways to merge pieces, or would you just not doing it?
So the question is, are there efficient ways to merge B trees? Yeah, so I'm not sure. I think that probably it ends up being similar to like a sort merge thing where if you have, you know, just think about it at the level of the leaf nodes, right? So you have one sorted array essentially over here, and you have another one over here, and you can kind of look at the first element, see which one's smaller, take that, and then take from each of those in order to build up the tree. Does that make sense? Sorry, I didn't. So the question is for the inner layers, you end up having to rebalance or split or merge things anyway, so does it end up being the same? Yeah, I think so. Starting from the leaf layer, since the data, the keys for each of the two trees, say emerging two trees for simplicity, the keys from each of those should already be in sorted order. So I think you can start at the leaf layer, fill out the leaves taking from each of the two trees, and then build up from there. There may be, and I am sure there is somewhere in the database literature work about efficiently merging two B trees or B plus trees at like the inner node part. I can try and track that down for next class, but I don't know of anything off the top of my head. But just from thinking about it for a second, I think you could certainly start from the leaf layer, and you already have two sorted key sets that you can pull from in order to do the merge. But that would still require building the inner nodes on top of it. Yeah. Yes.
The bulk insert means inserting a new table?
So the question is, does a bulk insert mean inserting a new table? A bulk insert means a bulk insert into the B plus tree. So it's essentially, imagine you have some pre-existing data. It could be stored in a table. It could just, imagine you have just a big array of integers or something. You want to build a B plus tree on top of that pre-existing data. So the way to do that, rather than starting from the root and kind of doing inserts one at a time, because then on every single insert we have to traverse the tree, find out where the key belongs, potentially do a split to make enough room in a new node, all that stuff. Rather than doing that, since we have this pre-existing data, if you just take the data and you sort it, then you can efficiently build the leaf node layers, because each leaf node is going to contain so many values, and then build the inner node layers on top of that until you get to the root. So imagine you have some pre-existing data, so it could be stored in a table, and you want to build an index, B plus tree index, on top of that pre-existing data. So it's like a bulk load into an index. Does that make sense? Great. Are there any other questions? Okay, so just to wrap up, the B plus tree is almost always a good choice for your DBMS. It is frequently used as both a clustered and non-clustered secondary index in a wide variety of systems. And as I mentioned, even though it's from the 1970s, it's still around and widely used today. And if you issue kind of a create index command in most systems, usually you will get a B plus tree behind the scenes. So with that, next class is going to be about index concurrency control. So if you have concurrent inserts or deletes on indexes, how do we make sure that those are thread safe? So if there are any other questions, we can talk now, or I have office hours right after this. So I will see you next week.
Yeah.
J, talking about the St. Ives brew. Run through a can or two. Share with my crew is magnificent. Plus it's mellow. And for the rest of the commercial, I pass the mic on to my fellow.
For a mic check, bust it. The B's all set to grab a 40. To put him to yoke and snap his neck.
St. Ives.
Take a sip and wipe your lips. Cue my 40's getting warm. I'm out, he got the dip.
Drink it, then I burp. After I slurp, Ice Cube, I put in much work. With the BMD and the E trouble, get us a St. Ives brew on the double.